At 9 o'clock, so maybe we'll start now.
Okay.
Okay. So thanks everybody for coming to this session. This is the first session on symmetric crypto. We have 3 papers in this session, and the first paper is computing the distribution of differentials over the nonlinear mapping chi. It is by Joan, Daemen, Alireza, Mehrdad, and Silvia, Mella from Radboud University, Netherlands, and STMicroelectronics, Italy. And the paper will be presented by Alireza, Mehrdad.
Yes. Thank you for the nice introduction. Hello, everybody. I'm Alireza, and I'm going to present this paper called Computing the Distribution of Differentials over the Nonlinear Mapping Chi. This is a joint work with Joan, Daemen, and Silvia, Mella. First of all, an introduction. So we start from scratch. Let's say we have a binary string that we call B, and this is like a 4-bit binary string, and we call it a circular string if we can consider this, the last bit and the first bit, as the neighbor of each other. So the first bit and the second bit are neighbors, and the second bit and third bit are also neighbors, and third and fourth. And if we can consider fourth and first bit as neighbors, then we call it a circular string. Then we define difference.
Can you please mute your microphone?
Yeah, please mute. Yeah, Alireza, you can continue. Yeah.
Yeah, okay. So let's say we have this string B and another string B star. Then what is the difference between these two strings? So the difference is defined as B minus B star. So because we are talking about binary string, then this minus here means the XOR of these two strings, which is this one. So from now on, I show the difference with the small letters. And then we define some terminology like active and passive bits. We call, if a difference bit is equal to 1, we call it active. And if it is equal to 0, we call it passive bit. And also Hamming weight, which is equal to the number of active bits in a difference. So here we have only 1 active bit. So the Hamming weight of this string is equal to 1. The next thing is differential probability and restriction weight. So let's say we have a function that is called alpha that works over f to the n, and then the differential probability of a differential, which is a difference before alpha and after alpha. The differential probability of this differential is equal to number of strings b in f2 to the n, such that the output of this string is equal to a. So if we put, if as input we give this function b minus b and b, then the output should be equal to a, and we count the number of these strings b and divide it by the number of total strings that can be have with f2 to the n. And this gives us the differential probability of this differential. And then we define another terminology, which is called restriction weight, and it is equal to minus log 2 of differential probability of b goes to a. The next thing is the mapping tree and how does it look like. This is how it looks like. So as an input, you have a string of L bit, and that is why we call it L. The string starts from B0, B1, and goes to BL minus 1. And 3 bits of the input do something and gives 1 bit of the output. And you can show this function as a local map of these three bits, bi, I plus 1, and I plus 2. So you first compute the NAND of bi minus I plus 1. Sorry, the NOT of bi I plus 1, and then AND it with bi plus 2. So like here, you compute the NOT of b1 and AND it with b2, and then XOR it with b0, and it gives you the 1 bit of the output. This is how this function GL works. And the question is how to compute the restriction weight for a given differential. So if you have a difference at the input of GL and a difference at the output of GL, what is the restriction weight of this string? Well, this problem is solved in 1991, and we say that because so Daemen said that because the mapping GL has degree 2, then given a differential BA, the weight or the restriction weight only depends on the value of the input B, and it can be computed as simply as this one. So if the input difference is fully active, then the weight is L minus 1. And if it's not fully active, then the weight is equal to Hamming weight plus 001 strings. I will give an example here. So let's say we have this string, then the because it's not fully active, then we should use this formula to compute the weight. And then the restriction weight is equal to the Hamming weight, which is the number of active bits, plus 001 string. So you have 001 string here. And because this is a circular string, we have also 001 string here. So all in all, we have 9 plus 2, which is equal to 11. So the weight of this string is 11. So the goal of our work is to efficiently compute the number of differentials with a given weight over GL. So if we have the weight and the length of the string, what is the number of this string that can have this weight? That helps us to have a comparison between the alternative nonlinear layer based on GL. For instance, we can use this parallel structure that uses a parallel GL that works on small circles, or we can use a parallel GL that work on a big circles, or we can use a single circle GL. So yeah, so the first one is used in some ciphers like Keccak and Zudu. The second one is used in radiogoton, and the third one is used in Subterranean. Okay, so the question is how to compute the number of differentials. Okay, to compute the number of differentials, we need to first define this function. So this function is called N, L, and W, and it computes the number of differences B with weight W at the input of GL. So because each difference B with weight W leads to 2 to the power W differences at the output of GL by definition, then it means that if we have the number of these differences, we can multiply them by 2 to the power W, and it gives us the number of differential over GL. But how to compute this N function? So it's not, so as I said, the restriction weight can be computed as by using these two formula. So it's easy to compute N for small or large W. For example, if W is 2, it means that we should have at least one active bit and 1001 string. So because it's not fully active, so we should use this one. And then it is one active bit plus 1001 string. So all in all, we have weight equal to 2. And since we just want to choose one position between L position, then the number of this string is equal to L. Or for a large weight like L-1, we can say that L-1 is equal to this one. So you can have the restriction weight equal to L-1 if it is fully activated. Or it can be like this. So Hamming weight is equal to L1, L-1, and you don't have any 001 string. So like this. So and you have only a single 0 at the string. And because you choose the position of this 0 between L positions, then we have L string of this shape. And the last one is this one. So when you have L-2 active bits plus 001 string, so which is here, and the total weight is L-1. But again, how to compute NLW for other cases? So for small weights or and large weights, it is easy. But what happens for other cases? For other cases, it's not easy to compute this NL. So we define another function that is called N3, L, H, and R, and it computes the number of strings with Hamming weight H, and that contains R001 string. So instead of looking at restriction weight, we look at Hamming weight and number of 001 string. And the sum of these two elements gives the weight. And if we sum all N3 over all possible value of R, then it gives us the value of NLW. So now we need to compute the N3 of L, the N3. So even N3 is hard to compute, but the thing that we can do here is to shorten the string of the input. And it means that we can delete or remove some bits of the input that doesn't affect the restriction weight. So the restriction weight is only depends on Hamming weight and 001 string. So as you can see, this is not an active bit, so we can remove it. And this is also not a 001 string, so it is only a 0, so we can remove it. So we call these two bits. So the first one we call whole, and the second one we call pause. So let's go on. We call a string without whole and pauses. We call it a minimal string. As an example, let's say we have this string and we want to generate a minimal string from this general string, original string. The first one is, so the first whole is this one. So this is between 2, 1. So we can just remove it. The second one is this one. We just remove it. And we don't have any other wholes. And the thing that we can do is to remove pauses from this string. And after removing all pauses, we got this string. That is a minimal string. And as a conclusion, we can say that the minimal string can be written as a sequence of 1 runs, that is a consecutive ones, and a string of 2 consecutive zeros. So you either have 2 consecutive zeros or 1, 1, 1, 1. Okay, so each string can be associated to a unique minimal string. And a set of string can be partitioned in classes. And a string in the same classes can be built by adding wholes and pause to the corresponding minimal string. It means that we can define another function, which is called N5, L, H, R, Y, and X that gives the number of string with Hamming weight H that contains R001 string, Y poses, and X holds. And then the value of N3 will be equal to N5, the sum of all N5s. But the question here is how to compute N5. So let's give an example first. So these are all possible strings with length 5 and weight equal to 3. So you can either have Hamming weight 3 and 0.001 string, or Hamming weight 2 and R equal to 1, and Hamming weight 2 and R equal to 1. For this, we can obtain these strings in the following ways. We can start with this minimal string, so 111, and then add 2 holes like this. Or we can start with these 4 minimal strings and add pauses. And also we can start with the same minimal string and add holes to them. So as you can see, there are something that is happening here. So for this blue one, you can either add 0 at the beginning or at the end of the string. And also for this violet one, you can either add 0 at the end or at the beginning. And that we observed, and we concluded that it is because of the value of the first and last bit of the minimal string. And because of that, we define another terminology that is called S, and it denotes the value of the first and the last bit of the string. Okay, and then from that, we define another function that is nmin HRS, and it gives the number of minimal strings with Hamming weight H or 001 string and given S. And then the number of ways that we can add X holes to this minimal string is can be computed with another function called alpha, and the number of ways that we can add pauses to this string, the minimal string, is called beta. And after all, we can compute the N5 by having a sum over all minimal string that can we can add pauses and holes to that. So I will not go into detail, but this is how this function looks like. So you can read it in the paper. So from N5, we can compute N3, and from N3, we can compute N, and from N, we can compute the number of differentials over GL. So as experimental results, so as I said, the number of differentials is like this. So in subterranean, we have G that works on 257 bits. And as you can see, the weight is going up constantly. But the reason that this graph going down is this part, this NLW, is going down. So after a while, it is going down. So. And we also had have a comparison between Zoodo. So in Zoodo, we have 128 parallel G3. But what happens if we only use a single circle G that works on all state bits? So this is the original one is showed by red, and the alternative nonlinear layer is showed by blue lines. So if we zoom at this part of the graph, we see something like this, and it shows that the number of differentials with if we use a single circle G is less than the original one. We also had this for Cuauhtemoc, Cuauhtemoc 400, and we had 80 parallel G5, and you can see that the difference is not is really negligible. And if we zoom on at this, you can see that the difference is so low. So as a conclusion, in this paper, we gave a method to compute the number of differentials with given dp over the nonlinear map L for any size of L. And we also provided number of differentials with given dp over nonlinear layer of subterranean. And also we have a comparison between Zudu, so the nonlinear layer of Zudu and Kerchak with their alternative nonlinear layer. And we concluded that in case of Zudu, if we have a single circle, then the advantage in the aspect of this paper is that the number of differentials is lower than the original Xi layer. And for Kerchak, this advantage was just negligible. And with this, I conclude my presentation. And if you have any question, I'll be happy to answer.
Yeah, thank you very much for this nice presentation, Alireza.
Yes.
Would anybody like to have a question? Yeah. Yeah, if not, then let me ask one, Alireza. It's a wonderful combinatorial analysis that you did and supplemented it very nicely with the experimental results also. So I just want to ask at a top level, do you think this result is going to be giving us some more insights about new kind of differentials we can look for or improve the existing differential attacks on Kerchak?
So about the differential attack, so the thing that I'm doing now is just this differential attack, and for that we search all possible trails. So it means that so this is only one nonlinear layer, but in the differential trail search, we search over like in Zudu we search over 6, and in Subterranean we search over 8 rounds of Subterranean. So we search all of these trails. So it doesn't help on that aspect, but it is helpful for designing new primitives. So it gives some insight about designing.
Yeah. Thanks, Alireza, once again for a very nice combinatorial analysis and a very nice presentation. Thank you very much.
Thank you. You're welcome. Thank you.
Yeah. So in this continuing this session, we will have the next paper titled Light-OCB, Parallel Lightweight Authenticated Cipher with Full Security. It is co-authored by Avik Chakraborti, Nilanjan Datta, Ashwin Jha, Cuauhtemoc Mancillas-L, and Mridul Nandi from different places. And Avik will be presenting this paper.
Thanks, Somitra, for the nice introduction. And I am sharing my screen. Oh, sorry. So can you see my screen?
Yes.
Yeah. Okay, let's start. Hello, everyone. I'm Avik from University of Exeter, and today I'm going to talk about our latest design called Light-OCB, which is a lightweight and parallel authenticated encryption scheme. And this work has been jointly done with Nilanjan Datta from TCG CREST, Ashwin Jha from CISPA, Mridul Nandi from ISI Kolkata, and Cuauhtemoc Mancillas-L from CINVESTAV-IPN Mexi. Let's go to the main part of the presentation. So as I've already told you that it is a lightweight and parallel authenticated encryption scheme. So why did we choose such property from a design? So definitely we should have some motivation. Let's check the motivation behind this work first. Yeah, the main motivation is to design something very efficient for client-server architecture, because nowadays most of the applications are based on client-server, and we have some additional motivation that the client side should be should consist of lightweight devices. So client-server architecture existed from the last 20 years, but client-server architecture with lightweight clients have actually come into the picture from the last like 7 to 8 years with the advent of lightweight IoT applications. So we have planned to design something which will perform both on the lightweight platform as well as it will perform very well in the high performance platform that the server wants. So for the high performance in the lightweight platform, we need to design something with that should have some implementation with low memory footprint, low latency. It should avoid some costly operations, and it should have some moderate throughput, because it's very hard to achieve very high throughput for a lightweight implementation. So we are happy with moderate throughput. Now the client side will encrypt and authenticate using this design, encrypt and authenticate the data packets using this algorithm. And similarly, the server side will also do the same thing using the same algorithm. So we also need something which will have an efficient implementation on the high performance platform too. That means it will have some implementation with low latency, high throughput, because server side doesn't care about the resource, but it cares about the speed of processing data, because it processes lots of requests from the client sides. So it should have high throughput, it should have sufficient memory, and it should have hardware acceleration property. Like we can have pipeline implementation for it, or we have parallelism in the structure, and so on. Now, our main question is, what if we need both? What we can do? Now let's check this picture. So let's consider some military application, used by the military. So they can have a high performance server with lots of resources, and consider lots of sensor-based devices. Now, these sensor-based devices constantly communicates with the server using intelligence data or other type of military data. So in that case, we need some algorithm that can be efficiently implemented in the sensor-based devices as well as in the server. And we also need that this algorithm will perform very well in both the platforms. So for that, these type of designs are very efficient, lightweight and parallel designs. And also there are numerous other applications. I'm not going to that in details. So what we need for lightweight devices and resource constrained devices, we need a lightweight algorithm. And for the server, we need a high performance algorithm, and parallel structure is an efficient structure to design high performance algorithms, right? So that's why we have adopted these two targets, like lightweight algorithm, as well as it should have some parallel structure. And there are many practical protocols that exist in the literature, like OML, WM2M, or co-op, and several others. Now, till now, I have mainly talked about the efficiency. Now, one of the most important property from a cryptographic algorithm is the security. So without security, we have nothing. So definitely, we need to set some security bound that we want to achieve from this design. And here we have actually played the safe. And if you know the NIST, National Institute of Standard and Technology in USA, they have initiated a lightweight crypto competition, and they have provided some recommendation of the security bounds. And our goal from this design is something which is suitable in both lightweight and high performance platform, as well as regarding security. It is security up to 2 to the power 50 bytes of data and 2 to the power 112 time complexity. Right? So this is the idea. This is the overall motivation behind our design. Now, this property, like this this parallel structure, has already been addressed by Philippe Rogawe, and he in CCS 2001 he has presented OCB, and this construction has got a lot of attention from the community. And yeah, so this construction has got a lot of attention from the community, and OCB actually is parallelizable, and it is highly efficient in software. But it has some issue that it needs a 128-bit block cipher and 128-bit key needed for the desired security. So it needs at least 256-bit state, 128-bit state register and 128-bit key register for that. And the overall state size is 640 bits, the overall state size. But though OCB got lots of attention from the community, but still, like lightweight and parallel algorithm didn't get much attention from the community until like the commencement of CISR, I can say. So in CISR, there have been several other proposals which achieve like parallel structure, like AES COPA or ELMD and others. And more importantly, in this lightweight crypto competition, several designs have been submitted, which are lightweight as well as parallel structure. And Locus is one of them, which directly defines the OCB for lightweight applications. Now, Locus actually optimizes OCB by adopting a 64-bit block cipher with an 128-bit key. So it reduces the state size by 64-bit. And also it reduces the overall state size to 336 bits from 640 bits. Well, the problem of Locus is it uses 2 calls to process one block of unit or one block of input. That means it has rate half. So that actually reduces the throughput of the construction Locus. So in this work, we have actually adopted the approach of refining Locus to design something that achieve higher throughput. And we actually design the construction Light-OCB that retains all the previous properties of Locus, as well as it achieves a rate 1. That means 1 call per block cipher to process 1 input block. Now, I'm coming to the specification. So both Locus and Light-OCB actually adopt this technique of using a nonce-dependent, generating an intermediate nonce-dependent key and nonce-dependent mask. So it adopts a tweakable block cipher in its design, and it processes the key and the nonce to design to compute a nonce-dependent mask and nonce-dependent key. And it divides this nonce processing phase into 2 domains. One is before nonce processing and after nonce processing. And what it does, it indicates the domains using the tweak values. So before nonce processing, the tweak value is 0. After nonce processing, the tweak value is 1. And this is a tweakable block cipher with a 64-bit block and 128-bit key and a very small tweak. Next is it goes to the associated data processing, where it actually follows the hash layer of the PMAC construction, and it processes the associated data with using a nonce-dependent mask and the nonce-dependent key with different tweak values. Right. So until the second last associated data block, it uses the same tweak value 2 for all the tweakable block cipher call. In the last block, it uses either tweak value 2 or tweak value 3, depending whether the last associated data block is full or not. And finally, it computes an intermediate state V XOR, which is a checksum of the outputs of the tweakable block ciphers. Next goes to the message processing phase. In the message processing phase, until the second last block, it uses the same tweak value 4, and it actually follows the structure of XCX that is used in OCB, and it masks the input, calls the tweakable block cipher, again masks the input with the nonce-dependent mask, and outputs the ciphertext blocks. In the last block, it adopts only the tweak value 5, because the domain separation, whether the last block is complete or incomplete, is taken care by this length of the message, length of the last block. So this length, if it is incomplete, it is less than 64. It is complete, then it is 64. So by incorporating the length, we can actually change the domains here. And finally, the message is processed to generate the ciphertext plus ciphertext block, and the checksum is also computed with the message blocks, and the associated data processing phase change, this V XOR and this M XOR are finally processed with a different tweak value to generate the final tag. This is the overall construction, and it has lots of similarity with both Locus and OCB. And ciphertext processing phase is actually the same, except is almost the same, except the ciphertext in the message ciphertext processing phase until the second last ciphertext block, we use the decryption inverse of the tweakable block cipher. So I'd like to say that this construction is not inverse free. So we need a separate circuit for the ciphertext processing phase and the message processing phase to when we implement the whole algorithm. Now I am coming to the choice of tweakable block cipher. Now, most of the tweakable block cipher based designs, the tweaks are used as counter for many of them. Now we have observed that so this tweak, so if the message size is long, then the tweak size should also be long to incorporate all the message lengths. So we need a much bigger register to store this tweak. So we have observed that we can have some short tweak TBC, where tweaks are not used for counter, but for different purpose. So in Light-OCB, we have actually used tweak to separate the domains. And you can see there are total 7 domains, 0, 1, 2, 3, 4, 5, 6, right? So for this, 3-bit tweaks are sufficient to separate all these domains. Now here, for the ease of implementation, we have adopted a 4-bit tweak. So this construction has actually been proposed in the ePrint paper. And this work has recently been accepted in the IndoCrypt 2021. And they say that they take a very small, very short tweak, they expand it with a high distance encoding to a larger tweak, and then inject this larger tweak to the block cipher state after every gap number of rounds. Okay. So, and overall, this is actually a framework that converts a block cipher to a tweakable block cipher. The lower part is the block cipher, the lower part. And in the upper part, we add a circuit to the block cipher to make it a tweakable block cipher. So we take a short tweak T of length small t, we expand it using an encoding to a large capital TE with length small te. And we inject this expanded tweak into TIC num cells in the block cipher state after every gap number of rounds. For example, we use gift 64 block cipher to convert it to a tweakable block cipher. In gift 64, the state is divided into 16 4-bit cells. So here we inject 1 bit to each of the cells, to each of the 16 cells. So that means TIC is 16. And we expand the tweak. Let's say in our example, in our case, we have taken a 4-bit tweak. So it is T0, T1, T2, T3. Each of the TIs are bits with a high distance encoding. Then we inject the tweak. And the expansion function looks like this. So T0, T1, T2, T3, it's to T prime, T prime, but T prime is an 8-bit expanded tweak. So this T0, T1, T2, T3 to T prime, it's a 4-bit 4-distance encoding. So T prime, it's an 8-distance encoding. Okay, this is the idea. And so we have directly taken this construction from the short tweak TBC paper in ePrint and the IndoCrypt paper. And the same construction has been used in the locus also. So we need a lightweight implementation. You can see that we just take a lightweight block cipher and we add some additional circuit. And actually, in fact, we actually reuse some XOR from the block cipher circuit. And we need only 7 XOR to compute this T prime. So overall, the overhead is very small. So we have a lightweight implementation. If we take a lightweight block cipher, we have a lightweight implementation, and we can use short tweak. Here we use 4-bit tweak, but 3-bit tweaks are sufficient, and it avoids unnecessary memory consumption to store the tweak. And we have linear tweak scheduling, no nonlinear function here. Now, what we have chosen gift 64 block cipher to convert it to gift 64 block cipher. We take a 4-bit tweak, we expand it to a 16-bit tweak, expanded tweak. We XOR each of the bits in this expanded tweak to each of the cell after every 4 rounds. Okay, so this is the overall idea of the tweak gift 64 block cipher, tweakable block cipher. Now, why Light-OCB is lightweight? So Light-OCB is lightweight because if we add up all the states, like we have the block cipher state, we have the key state, we have the checksum states, we have the state to store the tweaks, and we have some other additional state for the control unit. So adding up everything, we get only 336 bit of memory are needed for 336 bit registers are needed to store the overall state. And it is almost same as gift CUMB and HANA. We use a lightweight TBC, and this is the result from this paper. So we have directly adopted this result. And you can see that for tweak 64 encryption and decryption circuit. So both the encryption and decryption circuit and encryption only circuit, they do not differ much with the actual gift 64 block cipher. And the throughputs are also pretty closer. So the overhead is not much higher. And regarding security, we have actually proven the security in the ideal cipher model using Patera's H coefficient technique. And we have seen that for PRF security, we have data complexity up to 2 to the power 64 bytes, which satisfies the NIST criteria, and time complexity is up to 2 to the power 128. And for INCTXT, the same. So it directly supports the NIST criteria, and in fact, it is better than the NIST lower bound for the data, the security concern. And we have also provided some benchmarking with some of the existing designs. And some of the designs are actually implemented in ASIC platform, so we couldn't use them in our FPGA benchmarking. And we have observed that Light-OCB, area-wise Light-OCB is lesser than Locus AED and Locus AED, and but the GB, the throughput is much higher, significantly higher, is almost twice. And overall area and throughput both have been optimized, and it provides a much higher Mbps per LUT. And in fact, the area of Light-OCB is slightly higher than Lotus AED, but on the other hand, the throughput is much higher for Light-OCB. And for all the other parallel construction, with the known implementation result, we have a better hardware area, and as well as like a good value of Mbps per LUT and Mbps per slice. And I would also like to mention that, so we have actually Locus AED provides int RUP security, but Light-OCB actually cannot provide int RUP security because it has rate 1, and OCB-like structure can be broken against the int RUP attacks. And summarizing all the features, so it is lightweight. We have a small state size, and we use an ultra lightweight 64-bit tweakable block cipher, a tweakib64. It has high performance. It is single person fully parallelizable, and it achieves optimal security bound in the ideal cipher model, which is the D into T is less than 2 to the power 192, and individually D less than 2 to the power 64 and T less than 2 to the power 128. And it is suitable for both lightweight and high performance environment. And we would like to say that we are now trying to implement it on the parallel. We are now trying to get parallel implementation of Light-OCB, and we will provide results when we are done with the implementations. And here in this work, we have only shown the lightweight implementation of Light-OCB. And finally, it has very recently become the second in the Lightweight Cipher Challenge 2020 by the organized by Data Security Council of India and Ministry of Electronics and Information Technology, Government of India. And thanks a lot for allowing me to speak here. Thank you.
Yeah, thank you very much, Avik. Would anybody like to have a question?
Hi, Avik. This is Jodhpur speaking. I have one question. So you said that your goal is to make sure that the design is applicable to both lightweight framework and also for high performance framework, right?
Yeah.
But is it not true for any lightweight cipher that even if you just put them in a high performance server?
No, sequential feedback-based sequential ciphers are so so this design will provide much higher throughput than sequential feedback-based ciphers. So if you consider,
but do you have any, I mean,
yeah, like CIS, Gift CFB, like sponge constructions, all of them are sequential feedback-based construction. So so Light-OCB can be much better, much efficiently adopted on high-performance platform due to its parallel structure.
Okay. Also, I have one question on the area report that you have shown.
Yeah.
If you go to that table again. Yeah, so
Yeah.
this LUT and slice count that you have for on vertex 7, which is 6 input lookup tables, is it not little bit still high area for extreme lightweight considerations? Because
honestly, okay, honestly, this okay. So first of all, this is not very high. So 1128 is pretty low, and secondly, like most of the parallel constructions, they are slightly bigger in terms of hardware area than the feedback-based constructions. But the advantage of Light-OCB is it has 64-bit block cipher. Most of the feedback-based constructions, they actually have birthday-bound security. So to get to the 64, to actually achieve the NIST criteria, they need 128-bit block cipher. But Light-OCB has the advantage of 64-bit block cipher. So that's why it is comparable to the feedback-based designs. But I think it is pretty low. It is not that high. If you consider like there are some very ultra lightweight designs like Acorn, Jambu. So they are actually really lightweight. But other than these constructions, this is like pretty competitive, I think.
Okay, thanks for the presentation. I have no more questions.
Yeah, thanks, Avik.
Thank you.
One thing I would like to ask is, do you consider the cost of nonce generation also in your design while you were presenting this table?
Cost means like hardware cost?
Yeah, so how do you present, how do you compute nonce in this actual implementation? Or you are just assuming it's coming in as an input?
Okay, yes. So we assume that it comes on the fly. Yeah. So okay. So in the whole presentation, in the whole implementation, we actually assume that all the blocks come on the fly at each of the clock cycles.
And what about the security proof of this design?
Yeah, it is in the ideal Cipher model.
Okay.
It is not in the standard model, first of all, because it has non-dependent key. And also, so we have adopted actually the Patara's H coefficient technique to prove it. And we have achieved that the datacom D into T is less than 2 to the power 192, and D less than 2 to the power 64, and T less than 2 to the power 128. I have made a mistake possibly in this presentation. I have said that D less than 2 to the power 64 bytes, but it should be D less than 2 to the power 64 blocks. That means 2 to the power 68 bytes. Yeah. And then we have actually divided like various bad events, and we have counted the probabilities of them, and we counted the probabilities of good events, the good world and the bad world, and we added up them, and we got the desired security count.
What about extending this kind of a technique to beyond birthday bound security?
So this gets beyond birthday bound actually.
Oh, I see.
Yeah, so we have full security in the ideal Cipher model.
Okay.
Yeah.
Okay.
So it in fact has full security, not only beyond birthday. Yeah.
Okay. So thanks for a wonderful presentation, and congratulations for your getting a prize in the competition organized by DSCI and Ministry of Electronics and Information Technology. Thank you very much for this work and really practical design.
Yeah. Thanks, Somitra, for your nice speech. And okay, so thank you. I'm attending the conference then.
Thank you very much. Okay, so now we have a third paper by MILP based differential attack on round reduced warp. This is a paper by Manoj Kumar and Tarun Yadav from DRDO New Delhi, India. And we have a recorded presentation for this, which I will play now. Okay, so I'll need to share my screen first. One moment. I'll just share my screen so that it is easier. Okay.
Hello everyone. I am Manoj Kumar. This is a joint work with Tarun Yadav. We are working in Scientific Analysis Group, Defense Research and Development Organization, India. We are presenting MILP-based differential attack on round reduced warp. This is an overview of our presentation. First, we will discuss differential cryptanalysis and lightweight block cipher warp in brief. Then we will present MILP-based differential characteristic search for warp and a key recovery attack on reduced round warp. Differential cryptanalysis was proposed by Biham and Samir in 1990. It is one of the most popular form of cryptanalytic attacks. So in its basic form, for an input difference delta x, which is between two plain text x1 and x2, some output differences must occur more often than the other. So for a block cipher EK with input x and output y, this cipher is designed in such a way that its output is indistinguishable from random permutations. A differential characteristic is a pair of differences delta x and delta y, where delta x is the difference between the inputs x1 and x2, and delta y is the output difference between the ciphertext y1 and y2. Delta x tend to delta y with a very high probability. So high probability differential characteristics is the first and foremost requirement for a successful differential attack. Nowadays, block ciphers are designed with 64 or 128 bit block sizes. So we need automatic techniques to construct the differential characteristics. There are several automatic techniques. The first one was branch and bound based techniques, which was proposed by Mancillas in 1993. Those are mixed integer and linear programming based, set SMT and constraint programming based techniques. Recently at Crypto 2019, machine learning based automatic technique was proposed to construct the differential distinguishers. MILP based technique was proposed in 2012 by Mova and others to search the differential characteristics for block ciphers, and this technique is mostly used by most of the designers and cryptonists to evaluate the strength of a block cipher against differential and linear cryptanalysis. So high probability differential characteristics are also used in a key recovery attack against the block cipher. Now we describe a lightweight block cipher warp. This was proposed by S. Banik and others at SSE 2020. It is based on 32 nibble type 2 generalized physical network structure. It is designed to optimize the security and efficiency by designing the permutation over nibbles. Its block size is 128-bit and key size is also 128-bit. There are 41 rounds in warp. The designers of warp explain this design in various equivalent forms. We explain the L block-like equivalent form of warp, where 128-bit block is divided into 32 4-bit nibbles. There is no key scheduling algorithm in warp. 128-bit key K is divided into two 64-bit keys K0 and K1. In odd number of rounds, key K0 is used, and in even number of rounds, key K1 is used. So this initial permutation is used to get two 64-bit halves. Then 40 rounds are applied, where round constant are XOR with the X1, two nibbles in X1. Then S box is applied on the 16 nibbles in X0. Then after adding round key with the output of S box layer, nibble permutation is applied. Then rotation by 24 bits is applied on the X1. In the last round, nibble permutation and cyclic shift operations are not used. So these are round constants which are used in 41 rounds, where each constant is of size 4-bit. This 4-bit S-box is applied in the S-box layer of the warp, and nibble permutation is applied on the 16 nibbles. So differential characteristics search problem can be divided into two modules. So in first module, we minimize the number of active S-boxes in a differential characteristic. Then using this, we optimize the probability of differential characteristic in the second module. So we model the MILP problem for each module. So first, we generate and minimize the linear inequalities of nonlinear component of the S-box with S-box. Then we represent the linear components of the round function, namely nibble permutation, XOR operations, linear inequalities. We solve the MILP model to construct the differential characteristics using the optimization problem solvers which are available, that is Robi and Simplex. So we now discuss module 1, in which we minimize the number of active S-boxes. So first of all, we construct the difference distribution table of the S-box. So in VAR, the 4-bit S-box is used. So we get 16 cross 16 difference distribution table. We use SageMath tool, which uses S representation of the S-box to construct the linear inequalities to represent this DDT. So DDT of the S-box, warp S-box is represented by 239 linear inequalities, which is corresponding to the possible points in the DDT. But this number of inequalities are very large, so the problem based on this linear inequalities cannot be solved efficiently. So we need to reduce the number of inequalities so that we can solve the MILP problem efficiently. So we reduce the number of inequalities using the impossible patterns in the DDT. This approach was given by Sasaki and Todo. So we write a new system of linear inequalities, which is corresponding to each impossible pattern. So there are 239 inequalities and 159 impossible points in the DDT of S box. So the inequality which satisfies the impossible patterns is assigned 0, otherwise it is assigned 1. So we have an inequality corresponding to impossible pattern. For example, for R158, we have Z5 plus Z9 greater than equal to 1. So the objective function in this is to minimize the number of inequalities, and we select the inequalities which exclude the maximum number of impossible points. So by solving this system using Groby, we get 21 linear inequalities which are used in module 1 for reducing, for getting to minimize the number of active S boxes. Now in module 2, we optimize the probability of differential characteristics. So for this, we consider the possible difference propagations which are there in the DDT of our S box. So there are 3 possible patterns, 1 2 to the power minus 2 and 2 to the power minus 3. So we encode these possible patterns with using two extra variables P0 and P1. So we get 1304 inequalities using SageMath tool, and similar to the module 1, we reduce these inequalities and we get 20 linear inequalities which are used in the module 2 to optimize the probability of a differential characteristic. Now we model the linear layers of the block cipher. So in VAR, we have permutation operations, which is a nibble permutation. It is represented by just renaming the variables. We have XOR operations. So we represent them by inequalities by excluding the impossible patterns. So like in equation 2, it is given for single bit U and V, we get output W. So we exclude the impossible patterns and we express the XOR operation by linear inequalities. Now we construct the MILP model for the whole block cipher, in which the linear inequalities for substitution and permutation layers are used to model an MILP problem. And the objective function is the optimization of probability of differential characteristic, which is minimization of summation of probabilities 3 into P0 plus 2 into P1. Now solving this MILP model using Groby, we construct the 18-round differential characteristic by extending a 17-round differential characteristic. So first we form a 17-round MILP problem and we solve it, and we get a differential characteristic with 57 active S boxes and probability of 2 to the power minus 114. Now we extend this 17-round differential characteristic by adding 1 round at the top. So we fix the output difference of this 1 round characteristic as the input difference of this 17-round characteristic, and we get a 18-round differential characteristics with 61 active S boxes and a probability of 2 to the power minus 122. We also construct an 18-round differential characteristic without extending the 17-round differential characteristics. So we form an 18-round MILP problem and solve it using Groby. We get the optimal differential characteristic with 61 active S boxes and a probability of 2 to the power minus 122, similar to the previous case. So we have also constructed such 108 different differential characteristics with the same probability. We have also constructed a 19-round MILP problem for VARF and solved it to get the optimal differential characteristic. We obtained a differential characteristic with 66 active S boxes and a probability of 2 to the power minus 132 for 19-round VAR. We are not able to get a differential characteristic with 65 or less active S boxes. So this is the best differential bound for 19 round war. Now I invite Tarun to discuss the key recovery attack on 21 round war.
Thank you, Manoj. We have searched for high probability preparation characteristic. Now we will mount key recovery attack. A 16 round preparation characteristic with a probability of 2 to the power minus 108 is selected from the 18 round characteristic mentioned previously. We add 2 rounds at the beginning and 3 rounds at the end of 16 round preparation characteristic. This makes total 21 rounds for key recovery attack. In this table, question mark represents undetermined bits in the differential. As mentioned previously, the 128-bit secret key is represented in two 64-bit parts K0 and K1. Each of the K0 and K1 has 16 nipples and each nipple has 4 bits. K0 is used for odd rounds while K1 is used in even rounds. We guess the round key corresponding to the active S-boxes in the additional rounds. The round keys used in first, 19th and 21st rounds are from K0 and the nipples are 0 to 4, 7, 10, 11, 13 and 14. Similarly, the round keys used in the second and 20th round are from K1 and the nipples are 1, 3, 4, 7, 8, 10, 11 and 14. In total, 72 bits, which are 18 nipples of the round keys are used in these rounds, which are to be guessed. To mount key recovery attack, first we need to collect the data. We build 2 to the power n structure corresponding to fixed bits in the input difference delta 1. Each structure traverses the 40 undetermined bits in delta 1 and generates 2 to the power 79 pairs satisfying the differential. Total number of pairs generated by 2 to the power n structures are 2 to the power n plus 79 and each pair will meet the third round differential with an average probability of 2 to the power minus 40. The probability of obeying the differential after 19th round for the pair encrypted with the right key is 2 to the power minus 108. The number of pairs satisfying the differential with a right key guess after 19th round will be 2 to the power n plus 79 filtered by 2 to the power minus 40 again filtered by 2 to the power minus 108 which is 2 to the power n minus 69. Here we choose n equal to 73 to get at least 2 to the power 4 which is 16 right pairs under the correct key guessing. In the key recovery part, we guess the key bits corresponding to 18 impulse of the round keys. We construct 2 to the power 18 into 4, which is 2 to the power 72 counters for the possible values of the 72 key bits. We are left with 2 to the power 73 plus 79 minus 72, which is 2 to the power 80 pairs after filtered by 72 fixed bits in delta 22. Expected counter for a wrong key guess after filtered by undetermined bits in delta 1 and delta 22 is 2 to the power 73 plus 79 minus 72 minus 40 minus 56, which is 2 to the power minus 16, which is very low for a wrong key guess. The right place will be used for key guessing and a key with highest counter will be the correct key. Now we talk about attack complexity. There are 2 to the power n structures and 2 to the power 40 pairs can be generated in each structure. With n equal to 73, the data complexity of the 21 round differential attack on what becomes 2 to the power 73 plus 40, which is 2 to the power 113. As we need to store the counter corresponding to 72 bits of the key, the memory complexity of the attack becomes 2 to the power 72. In the first round, for each of the 2 to the power 80 pairs, we need to guess the 24 key bits corresponding to the 6 active S-boxes. Therefore, time complexity of the first round becomes 2 to the power 80 plus 24, which is 2 to the power 104. Similarly, the time complexity for second, 21st, 20th, and 19th rounds are 2 to the power 72, 2 to the power 96, 2 to the power 72, and 2 to the power 36, respectively. The time complexity of the whole attack is bounded by the 2 to the power 113 chosen plaintext. Here are some of the references that we have used in our paper. Thank you. Our source code for this attack is available at GitHub at the following link. In case if you have any queries or questions, you can contact us at these email IDs. Hello.
Yeah. Yeah, thank you very much for this very nice and detailed presentation on attacking reduced round of warp. Obviously, a lot of wonderful work was done in finding out this differential and so on. Somewhere you mentioned, Manoj, that you found an 18-round differential and with certain number of active S boxes, I believe 61. Can you have some more insight about, is it not possible to find a differential with lower number of active S boxes?
Your sound is not audible. Some echo is there. Repeat your question.
Yeah. Okay. So I was asking is that 1 minute. There is some I don't know. Some voice. Let me try.
It's fine.
Yeah. So hope you can hear me now.
Yes, sir.
Okay. So I was asking that you had shown first of all a wonderful work. You gave a very detailed attack on reduced round warp and used nice tools to actually develop this MILP based differential. You had shown an 18-round differential with about 61 active S boxes. So there was a comment about you couldn't find anything better than this. So do you have any intuition if you can have a differential of 18 round against warp, which has less number of active S boxes?
Sir, we designed an MILP problem for 18-round warp, and by solving it, we are not able to get any trail with better bound than the 61 active S boxes. So this was a best bound.
Okay. Yeah. So anybody else would like to have any question? Yeah. If not, then let me thank both the speakers once again and all the speakers of this session. But before we close, there is a question by Shikhar for Avik. So Avik, in case you are here, can you please read the chat and answer the question by Shikhar? He is asking you two things. First is about a recent attack on OCB2 from Crypto 19. Is it relevant to your design? Avik, in case you are here. Yeah, it seems
yes, I'm here. Yeah.
Okay, great. Please, can you please read the chat and answer Shikhar's two questions?
Actually, I'm here, so I can also just ask Avikda the question. Sorry, I could not ask the question during after the talk. So thanks, Avikda, for the great talks. I had just this question. So there was this attack in Crypto 19 on OCB2, right? So I was just wondering, since you said that Light-OCB is kind of inspired by OCB design and uses this XEX. So I was just wondering, like, is that attack relevant here at all?
Could you please repeat the question once more, Shikhar? It was breaking.
Yeah. So sorry. So I was just asking, there was this attack on OCB2 at Crypto 19, right? The best paper award at Crypto 19.
No. This attack is exactly that attack is not useful here because we have like nonce dependent key.
Okay. Thanks. Okay, cool. And the other question I had was, so in general, is post-quantum security of lightweight modes popularly studied, or have you looked at post-quantum security or
Not,
Light-OCB?
not really, but I think some sponge-based designs are actually used for post-quantum crypto, but I do not have much idea about like block cipher or tweakable block cipher-based designs.
Okay, because there are some known quantum superposition attacks on OCB, right? So I was just wondering whether that affects these lightweight constructions or not.
That maybe, but we didn't take it actually. So we will assess our design later.
Okay, cool. Thanks a lot. Okay, thanks.
Hello, Shikhar. This is Nilanjan.
Oh, hey, Nilanjan. Yes. Hey.
Yeah. So regarding this post-quantum security, I believe that would be an interesting task because the straightforward attacks like that can be mounted on PMAC or kind of OCB kind of structure. So here the problem is that there is a like this non-streaking. So that the similar attack won't work as it is, but whether some different attack comes up.
Okay. So you're saying that the basic attacks based on Simon's algorithm may not immediately work here because of this.
Those attacks may not immediately work.
Oh, okay. Thanks a lot. Yeah, thanks, and belated happy birthday.
Thanks for that.
Thanks.
Thank you.
Okay, thanks.
Okay. So it was a very nice session with all of the wonderful speakers and very good participation from others. I thank all the three presenters for this talk, actually 4 because the third paper was presented by both the authors, and very nice presentations. Thank you very much. And now you can continue with the next session. Thanks a lot. Bye-bye.
Thank you, Somitra. Thank you.
Thank you.
Hello. Is Moinak there? Or
Yes,
Laila?
I am here.
Okay.
So I guess this concludes our today's session. Hello, Devdeep, are you there?
Yeah, I'm there. So I think thanks all of you for this session today. And I agree that maybe we can switch over to tomorrow.
Exactly. So thanks a lot for joining today. It was great, especially during the tutorial and the paper session. I guess we'll continue tomorrow and more exciting things are in place.